So, in today's lecture, we are going to discuss first about equilibrium, and then we have to discuss about reversible processes, and we will do one example of a calculation, and then we will try to finish the reciprocity, reciprocity and cyclic relations. So let us see how much we can finish in this lecture. So equilibrium. So the book which is interesting to discuss this topic is by uh, Luskambe. I do not know if this is the right pronunciation of that, on thermodynamics. And so the idea of equilibrium is that there is no change with time, and thermodynamics um, gives you a sense of time in the universe also. So ideally, there is nothing in this world which is in equilibrium. So there was a question. There is a very nice explanation by on a YouTube channel uh, known as Veritasium, and on this channel you will find out a video on entropy. So we'll discuss entropy, which is another state variable. And this comes in the second law of thermodynamics. And the question he asks is that if you keep the bookkeeping law, that means energy is not being created nor destroyed, then what Earth gets from the sun? So, and the answer of that is the Earth not really gets the energy from the sun, because whatever amount of energy sun is providing to Earth cannot use all of it. So, because of the bookkeeping law, you will have some amount of work done and some amount of consumption of the energy. It cannot create energy. So it cannot get anything, right? Because Earth is also emitting energy, and all those things has to balance out. So, so then what is the actual gain from the sun which Earth gets? And the answer in that video is Earth gets from sun small packets of energy, and then uses that to uh, increase the increase that small packets to large packets, which is the idea of entropy. So I don't want to disclose much about entropy in this lecture, but it is related to that equilibrium, if the system is in equilibrium with, say, for example, surrounding, then why do we call it equilibrium? So equilibrium means that there is no change in the system or surrounding, if there are two partners or three partners. So then A to B, there is no change with what? With time. So for example, the amount of A, the concentration of A is not changing at all, and concentration of B is also not changing at all. Or for example, temperature is not changing. So if the things are not changing, the states are not changing with time, then that is what we call as equilibrium. And then how do you put mathematically? How do you put equilibrium in mathematics also comes from the second law, once we have the idea of entropy. So we'll come back to equilibrium when we discuss the second law. So with equilibrium, now we have to discuss the reversible processes and irreversible processes. So as the name suggests, that if you have a process where A converts to B, and you can convert B back to A, then that process is reversible. But then A to B change has happened in time. And from B to A, if you can go back without doing any change on the surrounding, then you are so the net result is zero, and that is an absolute ideal reversible process, and that cannot exist, that cannot happen. So there is no process which is completely reversible, but there are some processes which are very close to what you can call as a reversible process. So for example, if you think about say uh, right now, that is not the true statement to make, but let us say that the temperature of Earth is not changing. So that means Earth is in equilibrium with its surroundings. So it's an isothermal condition and temperature is not going to change. You can say this for Sun, for instance. I'm not so sure, maybe the temperature of Sun is also changing with time, but the time is so large for the change to be significant that you can call momentarily, you can call it in equilibrium. So you see that the idea that if something is very slow and the changes are insignificant with time, then those changes appear to be in equilibrium. Okay, so anything in this world will change, anything in this universe will change. The amount of time given for that change to happen. So, for example, if I so you have for example a bridge, okay, um, which is say made by steel wires. So you have wires like this which are holding the bridge, okay. So you will not see any change in the tension of the wire in say 100 years, but that doesn't mean that it is not going to change. So under the applied forces, if you give enough time to it, it is going to extend in length. Okay, it is going to deform permanently. But that amount of the time required for that maybe is greater than 1,000 years. And so you can say that the system is not going to change in the amount of time we are dealing with. And so you can call that in equilibrium. So so there is no reversible process, but there are processes which are very close to being reversible. And so one example is that if you put ice and water at 0 degrees Celsius, and then so suppose you have both ice and water at 0 degrees Celsius, and if you increase the temperature by a very small value, very, very small value, ice will convert to water. And then if you cool the water down by a very small value of temperature, it will change back to ice. Okay, so this appears to be a reversible process. Similarly, you can have another example of reversible process is it's a copper sulfate. When it reacts with zinc, it produces zinc sulfate and copper. So this happens because for this reaction, the E, so electromotive force, or you can say that the free energy, well, we have not also discussed the free energy. So let us say that the forward reaction is favorable under certain conditions. So you apply voltage and you connect them, and then this reaction, actually you don't have to do anything, you just have to put zinc and the reaction will go in the forward direction. But if you apply a reverse voltage, okay, and then what happens, that the reaction reverses, so it goes back, so then the backward reaction happens. Similar type of reaction you must have seen in, for example, um, in the reduction of iron in blast furnace. So where you see that CO2 reacts with the solid coke and it forms 2CO. So it converts to carbon monoxide. and this is called Woodward reaction. And then the reverse reaction can also happen, and carbon monoxide can convert to CO2 and C. So that reaction is called solid deposition reaction, and this reaction is called solution loss reaction. So there are chemical reactions which can go in backward direction and in forward direction, but you have to supply energy. So these are not really the reversible processes. They appear to be reversible processes, but in order to come back to the same position, so I'll give you an example of irreversible process, which will make you understand this. So irreversible process is, say that you have a container which has the walls which is adiabatic, so there is no change in heat. Okay, and you have gas in it. Okay, and the initial condition is that you have a pressure P naught and you have a volume V. So because this container is closed, so the volume is not going to change, and then you start stirring it. Okay, so you start stirring it with a very high velocity. You have kind of magnetic stirrer or something which moves inside, and then you start stirring, because of which the pressure increases from P naught to P1. Okay, the pressure increases, and whatever is the corresponding change in the internal energy will happen because of the first law of thermodynamics. But this cannot be reversed now. You cannot go back to from P1 to P naught without doing any additional work. You will have to do, in order to bring this back to P naught, you will have to give energy. So in order to come back to the original state, you need to supply energy to contain energy. Okay, and so these are irreversible processes. Irreversible processes, and almost all the processes are ideally irreversible, but there are processes which appear to be reversible, and they are used in thermodynamics for explaining a lot of things. The first idea of reversible process came from the Carnot's engine, which was very astonishing for a lot of people, that you can create an engine which can come back to its original position. So uh, so after doing this, let us do a very quick calculation example, just to have some practice of calculation. So let us take an example of a container in which we have a spring attached, and here you have a gas at a condition of pressure P naught and volume V naught. Okay, and this spring has a spring constant of K. So the question is that if you supply heat to from here, if you supply heat to the system, then by how much, so what amount of work is being done against the forces of the spring? Okay, this is one problem which I think I'll give it to you for trying out. So you need to calculate how much work is being done against the spring. Okay, and so you try doing that, and in the next lecture I will come back to the solution. So we'll do the solution in this in the lecture, in the next lecture. Okay, so right now let me discuss something which is called cyclic relationship and reciprocity, and then we have to go to the heat capacity definition. So, so let us say that you have a function f of, so you can define x as f of y and z, and you can define z as f of x and y, or you can have y which is a function of x and z. Okay, so let us take these two and then define dx. So dx is going to be del x by del y at constant z into dy plus del x by del z multiplied by dz, and this is at constant. This is at constant. So y, okay. So this is a function of y and z, so at constant y. Okay. Yes. Okay. So this is that. And then similarly, I can write dz as, so dz will be dz, so differential of z with respect to x at constant y multiplied by dx. This is basic chain rule of differentiation, and del z with respect to y at constant x multiplied by dy. Okay, so now let me put the equation 2 here, this dz here, okay, and see what happens. So then I can write dx is equal to del x by del y at constant c dy plus I will have here del x by del z at constant y, and dz I have to write, which is del z by del x at constant y dx plus del z by del y at constant x dy. Okay, have I done it correctly? I think so. Fine. So then what do we have? So then what do we have? We can take dx term together, right? So if I multiply this term with this term, I'll have dx, which I will bring on this side. So I will have dx into, so this becomes 1 minus del x by del z at constant y multiplied by del z by del x at constant y. And then I will have y terms, which also I bring on one side. And so these two y terms are positive, so it will become negative. So minus dy into, I will have del x by del y at constant z, and this will be added with this. So I will have del x by del z at constant y, del z by del y at constant x. Is there any other term with dy? No. So this multiplied by this goes there, and I have this, yeah. So I'll have this, right, equals to 0. So now for this is equal to 1 divided by del z by del x at constant y, and this is called reciprocity. Okay, and when we do this, when we change x, y, z to p, v, and t, then you will see that these equations are important and used in thermodynamics. So right now we just wanted to make reciprocity condition, which is this one, And then cyclic condition comes from this term when you put that equal to 0. So when you put this equal to 0, then you reverse this term and this term, and what you get is minus 1 is equal to del x by del y z into del z by del x y into del y by del z x. So basically this plus 1 is equal to 0. So this is called cyclic condition. Cyclic condition. Okay. So keep in mind the reciprocity condition and cyclic condition, and then we will use it in some of the equation when we discuss about the state variables in second law of thermodynamics. So that's it for today.